All right, guys, so today we're going to do our last lesson of the semester, theoretical and conditional probability. So let's kind of just jump right in. Theoretical probability is the probability, the measure of how likely an event is to occur. So the set of all possible outcomes is called our sample space. And to find equally likely outcomes, the theoretical probability of an event. So notice that I have a P from the word probability, and E here is the event, okay? And so this is going to look like a ratio. On top will be the number of favorable outcomes. On the bottom will be the total number of possible outcomes. So let's take a look at our example number 1. Okay. A jar contains 32 red marbles and 28 blue marbles. What is the probability that a randomly selected marble is red? So they want to know, this would look like P, and then the outcome would be red. So that's kind of what the notation will look like, okay? So we have 32 red and 28 blue. So we need to add those together to get our total, which I've done. That equals 60. And then the favorable outcome that they're looking for is for a red marble. So that is just going to be 32. Okay, so 32 over 60. And now I'm going to go ahead and reduce that fraction. And it will be 8 over 15. And that's it. I'm all finished. Okay, so that is about as simple as it gets. Let's look at example 2. 2 dice are rolled. What is the probability that the sum of the 2 dice on the next roll is at least 9? All right, so let's take a look. I made a chart on the back of my paper to help us understand all the different possibilities when we roll 2 dice, okay? So here is my chart, and I may need to zoom out for us. Okay, so this would be die 1. Now on a die, there are 6 sides, and they contain the numbers 1 through 6, okay? So that's the first die, that's the second die. If I roll 2 ones, the sum is 2. If I roll a 2 and a 4, the sum is 6. So I went ahead and I just made this entire chart for us. Now I'm looking for the possible outcomes that could equal a sum of 9 or higher. So notice it does like kind of create this nice little pattern. So the sum of 9 or higher would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different possibilities. And then, of course, how many total possibilities are there? 6 for the first die, 6 for the second die. So there are 36 total possibilities here. Okay. So I'm going to zoom back in now. So the favorable outcome that we're looking for is a sum of at least 9. So we just counted up that there's 10 different ways to get a sum of 9 or greater. And then the total number of outcomes is 36. Okay, so here's my notation. The probability of a sum greater than or equal to 9 equals, and then I'm going to reduce this fraction. 10 over 36 is the same as 5 out of 18. All right, and so that is my answer. So if you need to jot down that chart that I showed, I encourage you to do that. It can be really helpful. Okay. So that is the probability of an event happening that we want to happen. Let's take a look at the complement of an event. The complement of an event is the probability that the event will not happen. Okay, so since the sum of all probabilities in a sample space is equal to 1, then the probability of an event not happening, this is not happening, will be 1 minus if it had happened. Notice that all of my answers here are fractions, less than 1, okay? So if it was 100% chance that something would happen, let's say I had a bag that was full of nothing but blue marbles. So it would be 28. What would be the probability of pulling out a blue marble? 28 out of 28 equals 1. Okay, so the total probability, the biggest it could be is 1, 100%. So we're going to do that 100% minus the probability of it happening. So let's take another look at an example with dice. Okay, so 2 dice are rolled. What is the probability of not getting doubles? So we know that our formula is 1 minus. 1 minus. Now we know that when we roll 2 dice, the total number of probabilities, again, is 36. Okay, and then what are all the different ways that you can roll doubles? Well, there's only 6 numbers, right? I can roll double ones, I can roll double twos, double threes, fours, fives, or sixes. So the total number of options for rolling doubles is just there's 6 of them. So the probability of rolling doubles is going to be 6. So let's do 1 minus 6 over 36. And I'm just going to go ahead and do the fractions for us today. That will reduce to 5 over 6. And that is our answer. So dice are really common. Also, spinners are really common examples, okay? So we've got this spinner, and I do have a note here. If the spinner right here is spun, find the probability that it lands on a number that is not prime. This number that I've marked out here is the number 1. And then here's my note. 1 is not considered to be a prime number. It is a universal number. So we're going to leave that out. We're going to leave that out. Okay. So we know that we're going to have 1 minus the total number of spaces on this spinner is 16. And so let's count up the numbers that are not prime. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 numbers are not prime. I went ahead and highlighted in advance the prime numbers. Remember, prime means a number that can only be divisible by 1 and itself. Okay? So 1 minus 10 over 16. And when I reduce this fraction, I would get 3 over 4. 3 over 4. Okay. Next in our notes, I just want to point out, this jumps to example 11. I put some of our notes out of order just to make it be able to all fit on 2 pages correctly. So I'm actually going to switch to the second page now. I'm going to come back to this in a minute. Okay. And we're going to look at compound events right now. Compound events. Compound events can be independent when the outcome of one event does not affect the outcome of the other. So what I would do is take the probability of thing A happening and multiply that by the probability of thing B happening. All right, so let's take a look at that. A coin is tossed, then a day of the week is selected. So the coin being tossed is going to be thing A. The day of the week is going to be thing B. They want to know what is the probability of getting tails. So probability of tails. And then the probability of the day of the week that starts with the letter T. So when we flip a coin, there's only two options, heads or tails. So the total for the coin is 2, and only one side of it is tails. So the probability of that is 1 out of 2. We zoom in. The probability of a day of the week starting with the letter T. So we know that there's 7 days in a week. 7 days in a week. So let's see, there's Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday. So it's just 2 days of the week that start with T. And so we're going to multiply these two events together, and we come up with 1 over 7. 1 over 7 is the compound event of these two individual events that don't really affect each other. Okay? I'm just going to do two things, and what's the probability of both things turning out the way that I want? Let's look at this example down here with crayons. So I have a bag of 8 red crayons, 14 purple, 6 yellow, and 4 green. So the first thing I need to do is count up how many crayons do I have. Okay, so my total number of crayons is 32. 32. What is the probability that if a crayon is selected and then put back in and I pick another one out, that they will both be yellow? Okay, so this is with replacement, which is really important. So if I pick a crayon and it's going to be yellow, let's see, there were a total of 6 yellow crayons. So the probability of event A, picking a yellow crayon, is 6 out of 32. Then I'm going to put it back in the bag. Now, what if I pick another one, and again, I want it to be yellow? Well, I put that yellow crayon back in, so I still have 6 yellow crayons in the bag out of 32. Okay, and so now I'm going to go ahead and multiply these together, and I will get 9 out of 256. And so this is not a very likely probability that that would happen. Okay, let's try number 9. So what would be the probability of getting a green crayon? So I'll put a letter G here. There are 4 green crayons out of 32. So I'm going to pick the green crayon, and then I'm going to put it back in, and I'm going to pick again, and this time I want to see about a red crayon. There are 8 total red crayons, and since I put this green one back, I still have 32 in there. Okay, So if I multiply this together, what I'm going to get is, when I simplify it, it'll be 1 out of 32. 1 out of 32. Okay, so that is independent events. Because I put the crayon back in the bag before picking again, the effect of the second probability didn't have any changes to it, because the first probability, I put it back and I started all over. Now let's come take a look at a dependent event. Dependent events. This is when the outcome of the first event does affect the event that comes after it. Okay. So before I do this example with you, right back on our first page, I gave you a note, like an FYI. I know that not everybody likes to play cards, and so we don't all know the information about a deck of cards. So I just put this together for you. Every single deck of cards, and I'm sorry that this got cut off, they have 4 different suits. Okay, and if I zoom in on this color, there's a heart, a club, a diamond, and a spade. Or is that the club and that's the spade? Sorry, my eyes aren't so great. But there's 4 different suits. 2 of the suits are red and 2 of the suits are black. Okay? So the hearts and the diamonds are red. The clubs and the spades are black. Now, in each suit, they contain these cards, ace through king. If you add those up, that is 13 cards in each suit. So 13 times 4 is 52. There's 52 cards in a standard deck. All right, so now that we know that, each suit only has 1 queen. Okay, so let me go back to our second page. And now I feel like we're ready to answer this, okay? So a card is going to be drawn from a standard deck and not replaced. I'm not going to put it back. And then another card is going to be drawn. What is the probability of choosing a heart and then a spade? Okay, so the probability of a heart is going to be, well, there's 13 hearts and there's 52 total cards. Okay, and then I'm going to multiply that by my next draw. My next draw is going to be the probability now of getting a spade. So I'm going to put an S there. But here's the deal. I just drew a heart, so now there's no longer 52 cards in the deck. Now there's only 51. There's only 51 cards in the deck. All right, and then how many of them am I hoping that are left that are spades? Well, there's 13 spades. So that is the difference. The total is what changes when you do not replace the card or do not replace the marble. Okay? And so if I multiply this and simplify it, I'm going to get 13 over 204. All right? So that is a dependent event where what I did first is going to affect what happened next because I no longer have 52 cards in the deck. Okay? We're going to do the same marble or crayon question, but this time we're not going to put the crayon back. Okay? So, the probability of getting 2 reds. So the probability of getting a red the first time, not putting it back, and then getting a, whoops, that should be a P, and then getting a red again. So I'm just going to like square it so it looks different. I don't know. All right, so how many red crayons? There's 8 red crayons. And remember, there was a total of 32 crayons in our bag. Okay, 32. All right, so let's assume I picked a crayon and it was red. And now I'm going to keep it out of the bag and set it aside. How many red crayons are left in the bag? Well, now there's not 8 anymore. There should only be 7 left in the bag. And also because I kept it out, there's no longer 32 crayons. There's only 31 of them. Okay? So now let's go ahead and simplify this and get our answer. I get 7 out of 124. So that is my probability. All right, let's do this again, but this time we're going to do a purple and then a green. Okay, so the probability of purple and then the probability of green. So starting out with purple first, we know that there's 32 crayons. 14 of them are purple. Okay, I'm going to keep the purple crayon out. So now there's only 31 crayons there. But now I'm hoping to draw a green. Remember, there's 4 green crayons. The total of green crayons shouldn't have changed. Okay, multiply this out, and surprisingly, I get the exact same probability. 7 out of 124. Okay, awesome. So this is a compound event. Okay, when one event does not affect another, and then when one event does affect another. So I kind of tried to color code these, but my yellow didn't print so great over here. But that's how we work them. They're a little bit different, but not too different. Okay. Now I am ready to go back to the front side of my paper. And now we're going to talk about conditional probability. Conditional probability. So conditional probability is given that A and B, okay, given events A and B, conditional probability is the event that B occurs knowing that event A already occurred. All right? So this is the notation. It looks like division. And the way that I read this is the probability of B given A. Probability of B given A. And so here is what this formula looks like. And this is what we're going to use. Alrighty. So we are going to get started here with example 11. And I'm going to leave that formula up there for us so we can see it. Okay, so we're back to our standard deck of playing cards. What is the probability that Mitchell will draw a queen given that the card was red? Okay, so let's take a look at how we're going to write this. So, probability of event A happening, something that already happened, is that the card was red. So let's do the probability of a red card times the probability of a queen divided by, I'm trying to squeeze all this in, divided by the probability of event A, right? Given that A already happened. So down here is going to be the P of R again. So let's go ahead and plug in our numbers. So how many red cards are in a deck? Well, 2 of the suits are red, 13 and 13. So that would be 26. 26 out of 52 total playing cards. Okay, so that also goes on the bottom. 26 reds out of 52 total. All right, now what was the probability of one of those cards being a queen? Well, there's 4 suits, and each suit has 1 queen. So that's going to be 4 out of 52. So now what I need to do is go ahead and I'm going to use my calculator, multiply all of these fractions together, and reduce. And I will get 1 out of 13. We always want to reduce the fraction as small as we can. Okay? All right, let's do one more example like this. One more example. So I want you to kind of notice that given the probability of A is always going to be like the second piece of information that they gave us because A already happened. Okay? So a number from 1 through 100 is randomly selected. Okay, what is the probability that it is an odd number? Okay, so how many odd numbers are there in the numbers 1 through 100? Well, half of them. Okay, so 50 out of 100, 50 out of 100. So this is a odd number. Okay, that was the probability that happened first. Now, a number from 1 through 100 is randomly selected. Okay. Part of my word problem is missing. Yeah, this should also include something about the number being a perfect square. Okay, let's add that. A number from 1 to 100 is randomly selected, and I want this to be a perfect square number. That was a typo. Sorry about that. So the number's got to also be a perfect square. So I've got my perfect squares are 1, 2 times 2 is 4, 3 times 3 is 9, 16, 25, 36, 49, 64, 81, and 100. So there are 10 perfect squares whose answers fall between 1 and 100. So this is going to be 10 out of 100. And if I reduce and simplify this, the final answer is 1 out of 10, or 1/10 likely that would happen. Okay, so now let's go ahead and talk about two-way tables and two-way like relative frequency tables. You should have learned about relative frequency in Math 1. You learned about regular frequency in 8th grade. So just a reminder for you from Math 1, how do we convert from a frequency table to a relative frequency table? So following my arrows here, you have to know the total number, okay? These are the actual numbers. So let's read this problem here. A frequency table below shows the number of first class and coach class passengers on a plane who checked 1 bag, 2 bags, or no bags. All right, so that's what we're looking at. So these are the actual numbers of people. 16 first class people checked 2 bags. All right, so how do I take this frequency and turn it into a relative frequency? What I need to do is to divide. I need to divide. So let me get my calculator. I need to divide the frequency by the total. Okay, so that's how I get from here to here. So let's do 16 divided by 160. I get 0.1. Okay, I'm going to go ahead and fill in the rest of this table. Okay, and so I'm back. I have filled in the entire table. Everything in these 6 boxes, again, all I did was I took these total numbers, 12 divided by 160, and I got 0.075. Now, how did I get the totals here? I just added 0.1 plus 0.325 totals this, okay? Same across here and here, and then I added these 3 together to get the number totals on the bottom. When we have a relative frequency table, the grand total of everything put together should always equal 1, okay? All right, so now let's bring this in to talking about the probabilities that we have been discussing today. So, part A. What is the probability that a coach passenger did not check any bags? So I'm going to go to coach and I'm going to look for 0 bags. And there it is, 0.1125. And I want to convert this to a percent. So this is going to be 11.25%. All right, so that is A. What about B? Let's see. I am looking for a first class passenger this time that checked at least 1 bag. At least 1 bag. So I can't use 0. If it was 1 bag, it was 0.075. 0.075. And if it was 2 bags, it was 0.1. Okay, so now I just need to add these together. When I add them together, I get 0.175, which is the same as 17.5% of the passengers on that flight. Okay, awesome. So that should kind of be a review of Math 1, just with the notation. Okay, the notation is really all that's new so far. But now we're going to bring this in, okay? Our next 2 are called joint relative frequencies. It is the value in each category divided by the total number of values. So let's take a look at what that looks like. And notice that it's got this bar in the middle, okay? So we are looking for the number of coach class. Coach class. That checked one bag. Okay. So coach class that checked one bag is right here, 0.375. And then we need to divide that by the total number of passengers that checked one bag, which is 0.45. Okay. How do I know which one of the totals goes on the bottom? It's going to be the second piece of information. Okay. All right. And so now let's go ahead and simplify this. And I get 0.83 repeating, which is going to be the same as 83.3%. Okay. All right. And then here is our last problem for today. I'm looking for someone who checked two bags in first class. So two bags in first class is 0.1. And now the total number, because this came second, first class, so I'm going to get the total of first class passengers, 0.1875. 1875. So on the top, it is which box covers both categories. And then on the bottom, it is the second category total. All right. And this gives me 0.53, which is the same as 53%. All right. That is it for today, guys. I know that was kind of a big lesson. And it went out of order a little bit. I'm sorry about that. I just didn't want to waste paper for us. So this was theoretical probability, compound events, conditional probability, and frequency tables with probability of events. Okay. Now I do want to just kind of point out one more thing. I almost forgot. I have purple arrows going from frequency to relative frequency. To get frequency into a relative frequency, we divide by the total. If we want to go backwards, say I already have a frequency table and they want me to say how many passengers exactly that might have been, then I would need to multiply by the total to get back to here. Okay? So you can go back and forth between frequency and relative frequency. And that's it. No more lessons for this semester. We are going to start reviewing next. All right, until review time.